Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. It's 2 a.m. A major news site just featured your e-commerce store. Traffic jumps from 100 visitors to 10,000 visitors in 20 minutes. Your 3 EC2 instances suddenly hit 100% CPU. Response times climb. Requests begin timing out. Checkout starts failing. Revenue stops. That's the kind of capacity-driven outage Amazon EC2 autoscaling is designed to help prevent. Instead of keeping a fixed number of servers running forever, an autoscaling group can adjust EC2 capacity as demand changes within the minimum, maximum, policies, health checks, and other limits you configure. But there's an important word there: help. Autoscaling isn't magic. New instances still need time to launch and become ready. Maximum capacity can still be too low. EC2 might not even be the real bottleneck. Your database, cache, network, or another downstream service might fail first. So this video isn't just about CPU goes up, add servers. We're going to learn how autoscaling actually works. In Part 7, Elastic Beanstalk showed us how AWS can automate much of a web applications environment. Now we're going one layer deeper into one of the mechanisms that can sit underneath a scalable architecture: Amazon EC2 autoscaling. By the end, you'll understand how AWS adds capacity, replaces unhealthy instances, prepares for predictable traffic, and, most importantly, how to avoid scaling one tier while accidentally breaking another. By the end of this video, you will be able to explain how an Amazon EC2 autoscaling group keeps the right number of EC2 instances running. You will choose between target tracking, step scaling, scheduled scaling, and predictive scaling based on how the workload behaves, not by guesswork. And you will understand the difference between Amazon EC2 autoscaling, which manages groups of EC2 instances, and application autoscaling, which helps services such as ECS and DynamoDB adjust their own scalable capacity. Most importantly, you will spot the scaling mistake that creates outages and surprise bills, scaling the web servers while ignoring the rest of the architecture. Here's a simplified week of application traffic. Sunday night is quiet. Friday afternoon is busy. Demand changes constantly in between. One option is to provision enough EC2 capacity for the busiest moment you expect. That can protect you from some traffic increases. But it also means you're paying for that capacity during quieter periods. Suppose your peak requires 10 instances. During most of the week, the application may only need 2 or 3. Keeping 10 running all week gives you extra capacity, but much of it may sit idle. Go too far in the other direction and you create another problem. If you only provision enough capacity for normal traffic, a sudden spike may overwhelm the application before someone can manually launch more servers. That's the balancing problem. Too little capacity creates performance and availability risk. Too much capacity creates unnecessary cost. Autoscaling helps adjust capacity as demand changes within the boundaries and policies you configure. It won't perfectly mirror every movement in the traffic line. New instances take time to launch. Metrics take time to change. Scaling policies need time to respond. And your minimum and maximum capacity settings place boundaries around the group. The goal isn't perfect synchronization with traffic. The goal is enough capacity to meet your performance and reliability requirements without permanently provisioning for a peak that rarely happens. Before we talk about auto-scaling groups, you need to understand two different ways systems can scale. Vertical scaling means making one system more powerful, more CPU, more memory, more capacity inside the same machine. Think of a grocery store with one checkout lane. Vertical scaling is like giving that cashier faster equipment, so one lane can process customers more quickly. Horizontal scaling means adding more systems. Instead of one checkout lane, you open 4. In AWS, that might mean running additional EC2 instances and distributing traffic across them. The terminology you'll often hear is scale up for vertical scaling, scale out for horizontal scaling, and in the opposite direction. Scale down means reducing the resources of an individual system. Scale in means removing instances or capacity from a horizontally scaled fleet. Amazon EC2 auto-scaling primarily works with the horizontal model. When demand increases, the group can scale out by adding instances. When demand falls, the group can scale in by removing capacity according to its policies and settings. It doesn't normally respond to high CPU by turning one running EC2 instance into a larger instance type. Remember, vertical, vol, change the size. Horizontal, change the number. EC2 auto-scaling is primarily about changing the number of instances or capacity units in the group. An auto-scaling group, an ASG, is the boundary that manages a fleet of EC2 instances. You give it a launch template, which is the recipe for new instances. A launch template can define the AMI, instance type, storage, security groups, IAM instance profile, user data, network interfaces, and an optional key pair. Then you set 3 capacity values: minimum, maximum, and desired. For example, minimum 2, maximum 10, desired 4. The group works to keep its current capacity aligned with the desired capacity while staying within the minimum and maximum limits. If an in-service instance becomes unhealthy, the group can terminate it and launch a replacement from the current launch template settings. That is the self-healing part. But it only works if your launch template can create a healthy, fully configured replacement instance. Every auto-scaling group has 3 capacity values you need to understand: minimum, maximum, desired. Let's use a simple example. Minimum, 2. Desired, 4. Maximum, 10. Think of minimum as the lower capacity boundary. In this example, the group should not intentionally scale below 2 capacity units. That might exist because the application needs multiple instances for availability or because you know a certain baseline is always required. Next is maximum. That's the upper capacity boundary. Even if a scaling policy wants additional capacity, the group does not intentionally scale above that configured maximum. This makes maximum an important guardrail for both architecture and cost. Finally, desired capacity. Desired capacity is the current capacity target the group works to maintain between the minimum and maximum boundaries. If desired capacity is 4 and one in-service instance is determined to be unhealthy, the group can launch replacement capacity to work back toward that desired level. Scaling policies can also adjust desired capacity as demand changes. So remember, minimum, lower boundary, maximum, upper boundary, desired, current target. Those 3 numbers define the basic operating range of the auto-scaling group. Quick checkpoint. Your auto-scaling group is configured with minimum 2, desired 4, maximum 10. Question 1. Which number represents the group's current capacity target? Desired capacity 4. Question 2. Which value prevents the group from intentionally scaling beyond 10 capacity units? Maximum capacity. And question 3. If one in-service instance is determined to be unhealthy while desired capacity remains 4, what can the group do? Launch replacement capacity to work back toward the desired capacity. That's the basic auto-scaling mental model. Boundaries plus a target. Minimum and maximum define the operating range. Desired capacity defines where the group is currently trying to be. Quick recall check. In the min-max, desired setup you just saw, which value acts as your cost ceiling when demand spikes? Maximum. It is the upper bound the group is designed not to exceed. Two common policy types handle dynamic scaling in different ways. Target tracking is the simpler proportional model. You choose a metric and a target value, such as average CPU utilization near 50%, or a defined number of load balancer requests per target. The auto-scaling group adjusts capacity to keep the metric near that target. Target tracking works best when the metric behaves proportionally. As you add instances, the per-instance utilization or throughput moves in a predictable direction. AWS generally recommends it for metrics such as average CPU utilization or request count per target. Step scaling gives you explicit threshold and increment control. You create CloudWatch alarms and define different responses based on how far the metric crosses a threshold. For example, add one instance at 60% CPU, add 3 at 75%, and add more if the breach becomes severe. Use target tracking when you want the group to follow a utilization target. Use step scaling when you need precise, custom responses to defined alarm ranges. Some traffic patterns aren't surprises. They're on the calendar. Imagine your company knows that traffic increases every Monday morning when a weekly promotion begins. Historical monitoring shows the same pattern again and again. Instead of waiting for CPU utilization to rise after customers arrive, you can use scheduled scaling. A scheduled action changes capacity at a time you specify. For example, you might increase desired capacity shortly before the Monday morning traffic window begins. That gives the new instances time to launch, initialize the application, register with the load balancer, and become healthy before the demand arrives. Later, after monitoring confirms that the predictable demand window has ended, another scheduled action can reduce the planned capacity. The important idea is, scheduled scaling prepares capacity around known time-based demand. But scheduled scaling has a limitation. It only knows the schedule you configured. It doesn't know that your company was unexpectedly featured on national television. It doesn't know that a marketing campaign suddenly went viral. That's why scheduled actions are often combined with dynamic scaling. Scheduled scaling prepares for the traffic you expect. Dynamic scaling responds to the traffic you actually receive. So don't think, scheduled or dynamic, think, which combination best matches the workload? At 3 a.m., one of your web servers silently fails. Nobody is awake to restart it. The auto-scaling group can be Amazon EC2 auto-scaling monitors the health of instances in the group to maintain desired capacity. By default, it uses EC2 status checks. You can also configure the group to use additional health signals, including elastic load balancing health checks, VPC lattice health checks, EBS health checks, or custom health checks. A load balancer can stop routing new traffic to an unhealthy target. When auto-scaling determines that an in-service instance is unhealthy, it can terminate that instance and launch a replacement. Those are related but different jobs. The load balancer protects traffic routing, and the auto-scaling group protects fleet capacity. Make sure the health check grace period gives a new instance enough time to boot. Deploy the application and become genuinely ready before the group judges it unhealthy. Imagine CPU crosses a threshold, so the group launches a new instance. That instance takes time to boot, install dependencies, start the application, and register as healthy. If the scaling system counts that instance as fully ready too soon, metrics can become misleading. The group may overreact, adding capacity repeatedly or scaling in before the new capacity has had a chance to help. For modern target tracking and step scaling, the key stabilizer is instance warm-up. During warm-up, a new instance is not counted toward the group's aggregated metrics in the same way as a ready instance, and scale-in actions are held back while the new capacity becomes useful. Set the default instance warm-up from real measurements, boot time, application initialization, health checks, load balancer registration, and any startup automation. Cooldowns still exist, especially for older simple scaling policies. But do not treat a generic 5-minute cooldown as the universal fix. Target tracking and step scaling should normally use a well-measured instance warm-up instead. Quick recall check. What does instance warm-up help prevent after a new EC2 instance launches? It prevents the scaling system from treating a not-yet-ready instance as immediately useful capacity. That reduces premature scale-in and helps the group avoid overreacting while the application is still starting. The goal is not just to wait a random number of seconds. The goal is to give new capacity enough time to become healthy and useful. Here's the mistake that can still take down an application even when the auto-scaling group works perfectly. Traffic rises. CPU rises. Your scaling policy reacts. New EC2 instances launch. They become healthy. The load balancer starts sending traffic to them. From the perspective of the web tier, auto-scaling worked. But every new application server opens additional connections to the same database. More servers means more application requests. More requests mean more queries. Soon the database exhausts its available connection capacity or becomes overloaded. Requests slow down. Timeouts increase. The entire application begins failing. And EC2 wasn't the problem. This is one of the most important architecture lessons in this video. Scaling one layer does not scale the entire application. Every time you increase capacity in one tier, ask, what dependency receives more pressure next? Database, cache, queue, storage, downstream API, network? Auto-scaling solves a compute capacity problem. It does not automatically solve every bottleneck in your architecture. Reactive scaling responds after demand changes. A metric rises, a policy triggers, and then a new instance still needs time to launch and become ready. Predictive scaling helps when your application has recurring patterns. Amazon EC2 auto-scaling analyzes historical load data, forecasts future capacity needs, and can add instances before a regular increase in demand arrives. This is useful for patterns such as business hour traffic, recurring nightly batch work, or a daily event where application startup time would otherwise create latency. Predictive scaling is not a replacement for dynamic scaling. Historical forecasts cannot predict every surprise. Use predictive scaling for recurring demand patterns. Then keep target tracking or step scaling in place to respond when reality differs from the forecast. Think of dynamic scaling as a thermostat and predictive scaling as a calendar-aware forecast. Dynamic scaling reacts to the metric you are seeing now. Target tracking adjusts capacity to keep a metric near a target. Step scaling responds to defined CloudWatch alarm thresholds and increments. Predictive scaling looks at historical load patterns and forecasts when capacity may be needed in advance. Use dynamic scaling for real-time changes and unexpected traffic. Use predictive scaling when the demand pattern repeats and your application takes long enough to start that reacting afterward would be too slow. The strongest designs often use both. Predictive scaling prepares for the expected wave, while dynamic policies handle the unexpected wave. Which scaling approach acts ahead of a known, recurring traffic pattern, dynamic or predictive? Predictive scaling. It uses historical load patterns to forecast when capacity may be needed. Dynamic scaling remains important because it reacts to demand that is happening right now, including surprises the forecast did not anticipate. Here is the loop in plain terms. First, your application produces metrics in CloudWatch, such as average CPU utilization or requests per target. Then, a scaling policy interprets those metrics. A target tracking policy works to hold a chosen target value. A step scaling policy reacts when a CloudWatch alarm crosses a defined threshold. A scheduled action changes capacity at a known time. A predictive policy forecasts future capacity from historical patterns. The auto-scaling group changes desired capacity, then launches or terminates instances from its launch template while respecting the group's minimum and maximum limits. That is why scaling is not just watch CPU and add servers. The right policy depends on how the workload behaves and how quickly new instances become useful. Sometimes launching an EC2 instance isn't as simple as start instance, immediately send traffic. Your application may need additional automation before that instance is ready. That's where auto-scaling lifecycle hooks can help. Here's the important distinction. A lifecycle hook doesn't perform the work itself. It pauses the instance's lifecycle so your automation has time to perform the work. During launch, a lifecycle hook can place a new instance into pending. Wait. Instead of immediately moving into service, the instance waits while your automation completes whatever additional preparation is required. That might include installing or validating a monitoring agent, retrieving configuration, completing application initialization, registering with another system, or running a readiness workflow. Once the work is complete, your automation tells auto-scaling to continue the lifecycle. Lifecycle hooks can also help during termination. An instance can enter, terminating, wait. That gives your automation time to drain connections, collect logs, send a notification, deregister from another system, or complete cleanup work before termination finishes. Auto-scaling lifecycle events can be routed through services such as Amazon Event Bridge, which can then trigger automation using Lambda, SNS, SQS, or another workflow. But don't add lifecycle hooks just because they sound advanced. They introduce additional waiting and operational complexity. Use them when you have a specific action that must happen during launch or termination. And make sure your automation completes the lifecycle action, or the wait will eventually time out. Remember, the hook creates the pause. Your automation performs the work. Up to this point, we've focused on Amazon EC2 auto-scaling. That's the service that manages groups of EC2 instances through auto-scaling groups. But EC2 isn't the only AWS resource whose capacity can change. Other AWS services expose their own scalable dimensions. For many of those resources, AWS provides a common framework called application auto-scaling. For example, an Amazon ECS service can adjust its desired task count. A DynamoDB table using provisioned capacity can adjust its read and write capacity. Supported Aurora configurations can adjust reader capacity. The important point is, these services aren't creating EC2 auto-scaling groups to accomplish that scaling. They're scaling a capacity dimension that belongs to their own service. Application. Auto-scaling provides a common framework behind many of those scaling controls. So build this mental model. Amazon EC2 auto-scaling. Fleets of EC2 instances. Application auto-scaling. Scalable dimensions exposed by supported AWS services. The exact configuration experience can differ by service. Don't imagine one giant auto-scaling console where every AWS resource is controlled the same way. First, identify what resource actually needs to scale. Then use the scaling mechanism designed for that resource. Let's put these two models side by side. Amazon EC2 auto-scaling manages EC2 capacity through auto-scaling groups. You define things such as a launch template, minimum capacity, maximum capacity, desired capacity, health checks, and scaling policies. The group launches, terminates, and replaces EC2 instances to maintain the required capacity. Application auto-scaling works with supported AWS services that expose scalable dimensions. For example, an ECS service can change its desired task count. DynamoDB provisioned capacity can change its read or write capacity. The architecture distinction is simple. If the resource you're scaling is a fleet of EC2 instances, think Amazon EC2 auto-scaling. If you're adjusting a scalable capacity dimension exposed by another supported AWS service, think that service is scaling controls and application auto-scaling. Don't use the names interchangeably. They're related scaling concepts, but they solve different capacity management problems. Let's test the distinction. Question 1. You need to launch additional EC2 instances when your web tier becomes busy. Which model? Amazon EC2 auto-scaling. The EC2 instances belong to an auto-scaling group. Question 2. You have a DynamoDB table using provisioned capacity, and you want its read and write capacity to adjust with demand. Which model? DynamoDB auto-scaling, backed by application auto-scaling. Question 3. Your ECS service normally runs 4 tasks, but you want its desired task count to increase as demand rises. Which model? ECS service auto-scaling, using application auto-scaling. Notice the pattern. We didn't start by asking, which auto-scaling product do I remember? We started by asking, what resource needs more capacity? EC2 instances? EC2 auto-scaling? ECS tasks? ECS service auto-scaling? DynamoDB provisioned throughput. DynamoDB auto-scaling. First identify the resource, then identify its scaling mechanism. Here is the mistake that still takes down sites. A team scales EC2, watches new instances come online, and then the database runs out of connections. The web tier was not the only bottleneck. Auto-scaling one layer is not auto-scaling the whole application. Review the full path. Compute capacity, load balancer limits and target health, database connections and query performance, queue backlog, caching, downstream APIs, and network limits. For a relational database bottleneck, the fix may be connection pooling, RDS proxy, query and index optimization, caching, read replicas, Aurora reader scaling, or a different data access pattern. It is not automatically add database auto-scaling. For a queue-driven workload, measure backlog and processing rate. For a cache, measure memory pressure and hit rate. For a downstream dependency, define back pressure and failure behavior. The right question is not, what else can I scale? It is, which dependency becomes the next bottleneck when this layer scales? Let's turn the concepts into a practical workflow. In the Amazon EC2 console, open Auto-Scaling Groups. Select the auto-scaling group you want to configure. Before creating the policy, check the fundamentals. First, capacity boundaries. Verify the group's minimum, maximum, and desired capacity. Second, health checks. Confirm that the group is using the health signals appropriate for your architecture. Third, instance warm-up. Make sure the configured warm-up reflects how long a new instance actually takes to boot. Initialize the application. Register with the load balancer if applicable, and become useful. Now open the Automatic Scaling section. For a straightforward web application, a good policy to evaluate is target tracking. Choose a metric that represents useful utilization or throughput. That might be average CPU utilization or application load. Balancer request count per target. Then choose a target based on actual load testing and the performance buffer your application requires. Don't choose 50% CPU simply because you saw 50% in a tutorial. Your application's safe target depends on how it behaves under load. Amazon EC2 Auto-Scaling creates and manages the CloudWatch alarms used by a target tracking policy. Monitor those alarms, but don't manually edit or delete the alarms. Auto-scaling manages for that policy. If your workload follows a recurring pattern, you can also evaluate predictive scaling. Review the forecast before allowing the policy to change capacity. If you need explicit threshold and increment behavior, evaluate step scaling. In that model, you create the required CloudWatch alarms and define how much capacity should change for each breach range. Then comes the part beginners often skip. Test it. Generate safe load in a non-production environment. Watch the metric change. Watch the scaling policy respond. Watch the new instance launch. Measure how long it takes to become healthy. Verify traffic reaches it. Then watch what happens when demand falls and the group scales in. The workflow is capacity boundaries, health, warm-up, policy, metric, load test, observe scale out, observe scale in. That's how you validate auto-scaling rather than merely configuring it. Now let's look at the same mental model from the command line. You don't need to memorize every parameter. Focus on the sequence. First, define how instances should be built. That's your launch template. Once you have a valid launch template, the core auto-scaling group command is AWS Auto-Scaling. Create auto-scaling group. This creates the group. Your command needs information such as the auto-scaling group name, the launch template reference, minimum capacity, maximum capacity, desired capacity, and where the instances are allowed to launch. After creating the group, verify it with AWS Auto-Scaling. Describe auto-scaling groups. This lets you inspect the group's configuration and current state. Check minimum, maximum, desired, current instances, availability zones, health, and the launch configuration being used. Then, when you're ready to attach a dynamic scaling policy, use AWS Auto-Scaling Put Scaling Policy. That command can be used with supported policy types such as target tracking, step scaling, or predictive scaling. For target tracking, Amazon EC2 autoscaling creates and manages the related CloudWatch alarms. For step scaling, you create the CloudWatch alarms that invoke the scaling policy. So the CLI mental sequence is launch template, create group, verify group, attach scaling policy, monitor health and metrics. The exact parameters and available options can evolve. Use the current AWS CLI reference when you're building the real command. Don't memorize a giant command from a video. Understand what each command is trying to accomplish. AWS autoscaling, create autoscaling group. AWS autoscaling, describe autoscaling groups. AWS autoscaling, put scaling policy. Quick recall from the last scene. Which AWS CLI command creates an Amazon EC2 autoscaling group? AWS autoscaling, create autoscaling group. Remember that the group needs more than 3 capacity numbers. It also needs a valid launch template or another supported instance launch definition and a placement configuration for the instances. A scaling policy needs a signal, but the signal depends on the policy type. With step scaling, you create CloudWatch alarms. For example, average CPU remains above 70% for 5 minutes. When the alarm enters the configured breach state, the step policy applies the matching capacity adjustment. With target tracking, you choose a metric and a target value. Amazon EC2 autoscaling creates and manages the CloudWatch alarms that help keep the metric near that target. With scheduled scaling, a scheduled action changes capacity at a time you specify. No alarm is required. With predictive scaling, the policy forecasts future demand from historical data and can add capacity ahead of an expected increase. The lesson is simple. Do not memorize one trigger chain for every scaling policy. Choose the policy model first, then understand what signal drives it. A few habits separate a clean scaling design from a surprise outage or surprise bill. First, spread a production autoscaling group across multiple availability zones when the application and network design support it. That reduces dependence on one failure domain. Second, use a launch template that can create a fully healthy instance without manual repair. Include the correct AMI, IAM role, security groups, user data, dependencies, application configuration, and observability setup. Third, measure instance readiness and set a default instance warm-up that reflects reality, boot time, application initialization, health checks, and load balancer registration. Do not begin with a generic cooldown value and assume it fits every workload. Fourth, configure health checks deliberately. EC2 health checks are the starting point, but a web application behind a load balancer may need the group to replace instances that fail, enabled load balancer health checks as well. Fifth, if you use mixed instances or spot capacity, diversify across appropriate instance types and availability zones. Design for interruption and use capacity rebalancing where appropriate. Finally, tag the autoscaling group and the resources it creates. Tags make cost allocation, ownership, and incident response much easier. Let's finish the technical section with 5 mistakes that cause confusion in both certification questions and real environments. Mistake 1. Using launch configurations for a new design. Launch configurations are legacy. For current EC2 autoscaling designs, use launch templates. They provide the instance recipe the autoscaling group uses when launching new capacity. Mistake 2. Thinking auto-scaling only responds to high CPU. Scaling policies can respond to different metrics and patterns. And the auto-scaling group also helps maintain desired capacity by replacing in-service instances that it determines are unhealthy. Mistake 3. Treating EC2 auto-scaling and application auto-scaling as synonyms. They're not. Amazon EC2 auto-scaling manages EC2 instance groups. Application auto-scaling supports scalable dimensions exposed by other supported AWS services. Mistake 4. Thinking auto-scaling makes one EC2 instance larger. EC2 auto-scaling normally works horizontally. It adds or removes instances or capacity units from the group. Mistake 5. Manually building the alarm workflow for every target tracking policy. With target tracking, EC2 auto-scaling creates and manages the CloudWatch alarms used by the policy. Step scaling is different. With step scaling, you create the CloudWatch alarms that invoke the scaling policy. These distinctions matter on CLFCO2, but more importantly, they matter when you're designing and troubleshooting real AWS environments. True or false? An auto-scaling group can automatically replace an in-service instance that it determines is unhealthy. True. By default, the group uses EC2 health checks. You can also configure additional health sources, such as elastic load balancing health checks, to help the group identify instances that should be replaced. The replacement instance is launched from the group's current launch template settings, which is why a reliable launch template is the foundation of a self-healing fleet. The cost-benefit of auto-scaling is easy to oversimplify. You might hear, auto-scaling means you only pay for exactly what you use. That's not quite right. Amazon EC2 auto-scaling helps you adjust EC2 capacity as demand changes, so you don't have to permanently operate a fixed fleet size for a peak that rarely happens. But you may intentionally keep capacity available even when it isn't fully utilized. Why? Reliability, performance, startup time, availability requirements, minimum capacity, scheduled actions, predictive forecasts, instance warm-up, and protection against sudden demand. All of those can influence how much capacity remains running, so the goal isn't always run the smallest possible number of instances. The goal is maintain enough capacity to meet reliability and performance requirements without carrying unnecessary idle capacity. And remember the architecture effect. Every additional application server can increase pressure on databases, caches, queues, storage, APIs, and network resources. So, scale thoughtfully, test the policy, watch the metrics, measure the dependencies. Auto-scaling isn't just a cost feature, it's a capacity management and reliability tool. Let's bring the entire lesson together. Takeaway 1. Understand the auto-scaling group. Amazon EC2 auto-scaling manages groups of EC2 instances. The group uses a launch template, minimum capacity, maximum capacity, desired capacity, health checks, and scaling policies. Together, those components help maintain the EC2 capacity your application needs. Takeaway 2. Match the scaling policy to the workload. Use target tracking when you want a metric to stay near a target. Use step scaling when you need explicit responses to alarm ranges. Use scheduled scaling for known time-based capacity changes. Use predictive scaling when historical patterns can help prepare capacity before recurring demand arrives. And combine approaches when the workload requires it. Takeaway 3. Scale the architecture, not just the servers. EC2 auto-scaling manages EC2 fleets. Other AWS services use their own scaling controls and, where supported, application auto-scaling. Every time one tier scales, ask, Which dependency becomes the next bottleneck? If you remember those three ideas, you understand the architecture behind auto-scaling, not just the vocabulary. Now turn this lesson into something you can actually demonstrate. Build a small non-production auto-scaling lab. Before creating anything, check current AWS pricing and free tier information for your account and region. Don't assume that EC2 instances, load balancers, public IPv4 addresses, data transfer, logs, or other supporting resources are free. Then create a launch template. Configure your instance so it can become healthy without manual intervention. Next, create an auto-scaling group. Start with a small capacity range appropriate for a lab. Spread it across multiple availability zones if your lab design supports it. Then, add a target tracking policy. Choose a metric you understand. Configure realistic instance warm-up. Now test 3 scenarios. Test 1. Demand increases. Generate safe load and observe scale-out. How long does the new instance take to launch and become useful? Test 2. An instance becomes unhealthy. In a safe lab, observe how the group works to maintain desired capacity and replace unhealthy capacity. Test 3. Demand falls. Observe scale-in. Which instance terminates? How long does the process take? Then document the architecture. Include launch template, auto-scaling group, minimum, maximum, and desired capacity, scaling policy, health checks, instance warm-up, CloudWatch metrics, and the dependencies your application would pressure as the fleet grows. That's no longer just certification study. That's a portfolio lab you can explain in an interview. You now know how Amazon EC2 auto-scaling adjusts capacity and replaces unhealthy instances. But adding servers creates another question. How does traffic know where to go? That's where the next lesson comes in. Elastic load balancing. We'll look at how AWS distributes incoming traffic across healthy targets, how load balancer health checks work, and how elastic load balancing and auto-scaling work together to keep traffic away from unhealthy instances while maintaining capacity. That completes one of the most important AWS web architecture patterns. Load balancer in front, auto-scaling group behind it, multiple availability zones for resilience. If you're studying for CLFCO2, continue through the series in order and use the current AWS exam guide and AWS service documentation as your source of truth. And don't just watch the lab. Build it. Break it safely. Watch the metrics. Troubleshoot it. Document what happened, then explain why. Because careers aren't built by watching videos. They're built by applying what you learn. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities. From EC2 basics to instance types, pricing, Lambda, containers, elastic beanstalk, and now auto-scaling, this series builds the exact working knowledge the CLFCO2 exam tests. Up next, load balancing. Use the playlist in order to prep without gaps. I'll see you there. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.